Let's talk about one of the biggest, most exciting, and honestly, most humbling quests in all of science, the hunt for a picture of another Earth. This is a story about incredible discoveries, mind-bending challenges, and just the sheer audacity of human curiosity. I mean, it's wild to think about. In just the last few years, we've gone from wondering if there were other planets out there to knowing there are thousands. Missions like NASA's TESS, the Transiting Exoplanet Survey Satellite, are just vacuuming them up, finding new worlds at an incredible rate, and filling our catalogs with this amazing zoo of planets. And that's the big question, right? It's one thing to know a planet is there because you saw its little shadow pass in front of its star. It's a whole other thing to actually get a picture of it, to see it as a place. So let's dive into that huge gap between finding and seeing. And we'll start with some really cool news. Just recently, NASA announced a discovery of a world that is seriously tantalizing. I mean, this planet checks a whole lot of the boxes we get excited about when we're searching for life. So let's meet TOI 715b. Okay, so this isn't just any old planet. TOI 715b is what we call a super-Earth, a rocky world bigger than our own, orbiting a red dwarf, which is the most common type of star in the galaxy. And here's the key. It's in the conservative habitable zone. That's a much stricter definition of the Goldilocks region, which makes it a really, really good candidate for having liquid water. But what really pushes this planet to the top of the list is its year. It's only 19 days long. Think about that. That means from our point of view, it passes in front of its star all the time. And every single time it does that, the James Webb Space Telescope can stare at the starlight filtering through the planet's atmosphere, looking for those chemical fingerprints that could tell us what that world is actually like. Discoveries like TOI 715b are amazing for sure, but they always lead to that next logical question. So, can we get a picture? Can we actually move beyond just detecting a world and resolve it into a place, with features? And this quote from a recent research paper just nails it. The whole goal of exoplanet science is shifting. It's not just about finding those little dots of light anymore. It's about tackling that much richer question. What does that world look like? Does it have oceans? Does it have continents? Are there clouds? Now, let's be really clear about what we mean by a picture. We're not talking about some high-res Google Earth-style image. The holy grail for astronomers right now is a simple 10 by 10 pixel image. 100 pixels, that's it. Just enough to go from that single point of light we can detect now to a super blurry map that might show us the most basic features of another world. But getting even this humble little image throws two of the biggest challenges in all of astronomy right in our face. Okay, so problem number one is all about simple physics and a scale that is just mind-bending. It's called angular resolution, basically a telescope's ability to see fine detail. And the detail we're trying to see is unimaginably tiny. Just look at that number, 162 kilometers. For my friends in the US, that's about 100 miles. Let that sink in. So what is that number? Well, to get that simple 10 by 10 pixel image of an Earth-like planet that's relatively nearby, the laws of physics say we would need a single space telescope with a mirror 162 kilometers wide. That's an engineering challenge that it's almost impossible to even comprehend. And this chart just illustrates the gap perfectly. On the far left, that tiny little sliver is the mirror on the James Webb Telescope, an absolute triumph of engineering at 6.5 meters. Next to it is a super ambitious future concept called LUVOIR A, with a proposed 15-meter mirror. And then, all the way on the right, is the 162,000 meters that physics says we need. We're not just a little bit short. We are orders and orders of magnitude short. Okay, but let's just pretend for a second that we could somehow solve that size problem. We'd still slam right into a second, equally massive challenge, something researchers call photon starvation. We are basically hunting for the faintest possible flicker of light in an endless dark ocean. Think about it. A planet like Earth doesn't make its own light, right? It just reflects the light from its star. And from dozens of light years away, that reflected glow is just unbelievably weak. We're not just collecting light. We're trying to catch individual particles of light, photons, one by one by one. 0.04. That number right there, that defines this whole second problem. Even if we had a giant telescope, for just one of our 100 pixels, we'd only collect about 0.04 photons every second. That's one single particle of light hitting our detector every 25 seconds. Trying to build an image with that little trickle of information, it's like trying to fill an Olympic-sized swimming pool with a single eyedropper. It becomes less a question of technology and more a question of just time. So, given these two absolutely colossal problems, the size gap and the light famine, how do our most creative, most ambitious plans for seeing another Earth actually hold up? Let's take a look at what the scientists have dreamed up. One of the most promising and, frankly, coolest ideas is the external star shade. The concept is just wild. You launch this huge, specially shaped screen, like a 50-meter-wide metal sunflower. Then you fly it tens of thousands of kilometers away from your space telescope. And then you have to align them both with insane meter-perfect precision to block the blinding light of the star so you can see the faint little planet next to it. It's an absolutely incredible feat of formation flying. But here it is. Here's the brutal reality check from the research. To get that one single 10 by 10 pixel image, even our most powerful proposed space telescope would have to stare at that one spot for almost 2,000 years. The super elegant starshade idea still takes about 230 years. Our biggest ground-based telescopes, almost 300 years. The numbers are just, they're stark. Our very best ideas would take centuries, if not millennia, to get the job done. So where does that leave us? Well, it means we have to really appreciate what we can do right now. Finding worlds like TOI 715b and using the Webb telescope to sniff their atmospheres, that's a revolutionary leap forward. We're moving from just counting planets to actually characterizing them. And that is the absolutely critical groundwork for what is clearly going to be a much longer, multi-generational journey. And this is the core conclusion from all that deep dive research. Is totally unambiguous. With the physics we know and the engineering ideas we have on the drawing board today, not a single one of them can give us that first blurry picture of another Earth within a human lifetime. The challenge is just that big. But this isn't a story about defeat. It's a story about a grand challenge. It clarifies the sheer scale of the mountain we have to climb. And it tells us that the answer probably isn't going to come from just building bigger versions of what we already have. Which leaves us with this incredible question. What new breakthrough, what new kind of physics or technology that we haven't even dreamed of yet will be the thing that finally turns that little dot of light into a new world? That, right there, is what makes this one of the most exciting things in all of science. Thanks for joining me.